Okay.
I don't know. No.
So what's going on here? Do we have thieves and thugs and hyenas here?
No, I must have taken it back to Iowa and then for yeah, I don't. No, he's got his own. He's got his own.
Your grandma must have stolen it.
Yeah.
What would she do
I'll
then?
catch her this time. Yeah.
Oops, we're recording here. Okay. Do you guys remember what we did last time? We had a service, a service panel that's supposed to be 3 panels, and we are to do step-by-step load calculation for this service, right? So I'm going to walk you guys through what we have done. So the building is 50,000 square foot commercial building, powered with 28120 3-phase 4-wire. And we're bringing all these numbers that you're looking at. Can you see these numbers, 1 through 5 through 6? We need to size them. So later on, when you see 1, size 1, these are the numbers I'm referring to. Let me go over it one more time. So starting with 1, guys, that's the box. The first box is called the service panel. The second, number 2, is the overcurrent protection device for the service panel, the breaker. Number 3 is the service entrance conductors. Number 3 right here is the service entrance conductors coming in, the phases. Number 4 is the neutral. Can you see that? That's a neutral. Number 5 is something called main bonding jumper. You are required by code when you bring the neutral from the utility to bond it to the ground for stability and to get rid of transient and to stabilize the neutral. Major thing that you have to do. Every time when you bring the neutral, guys, the first thing you do, take a wire and tie it to the ground via a ground rod or the steel of the building or a bunch of other things there. Any metallic contacts, any metallic object in direct contact with earth. That's 5. That's the main bonding jumper. Then number 6 is the wire that you take it from the ground bar inside the panel. There's a bar. That's a ground bar. You take it and you bond it to the ground rod. That's number 6. This guy here is symbol for the ground. Okay, so that's number 6. Then we're going to go down. That's a service. Right underneath it, guys, the feeders. Can you guys see these 3 feeders coming to 3 panels? We talked about feeders versus service at the top, feeder at the bottom. All these feeders, you guys are going to size the following. Number 1, you need to size the panel itself. That's all. So you're going to size, how many panels do we need to size here? 3 panels. RP, LP, and MP, receptacle, light, and mechanical. Then number 2 is the circuit breaker that protects the panel, the receptacle panel. And also, we're going to have one for the lighting panel and one for the mechanical panel, right? Number 3 is going to be the conductors, the feeders, the size of the feeders, right? The same thing for receptacle, light, and mechanical. Number 4 is the neutral. With every feeder to a panel, guys, come a neutral, right? You have to have a neutral. Now, everybody understand what a 3-phase 4-wire system is. When you get design commercial, you almost always you're running with so-called 3-phase 4-wire. So, my friend, the first 3 conductors, the 3 wires are the HOTS, A, B, C, phase 1, 2, 3, and what's the last one? The neutral. Okay. So that's basically what we're going to be doing. 50,000 square foot. So I'm going to walk you guys. Now we did that. Now and the panels, remember we talked about receptacles, guys, multi-out assemblies, light, show window, track light, sign, parking lot lights. These are given. And we did the calculation, heating, chiller, motors, and kitchen equipment. And we did all the calculation for the receptacles, and we came up with, after we derate them with 56.9, then we did the lights, and after we derate them, we came up with all our lights, track and everything else. We came up with lights of 2.5. Then we went into the heating and cooling. We picked the largest of heat and cool, and we came up with 89. Am I going? You guys are. This is a review, right? Okay. Then we went to the motors, and we came up with a size of 70 kVA.
For the lights, set 2.5. We're down at 242.5.
For lights, let's go back to the stipple lights. All lights, 242.5. What did they say?
I thought you said 2.5 first. I could have just heard you.
You could, we can rewind.
Uh-oh.
Nobody cares. We get. So 242.5. That's a light. The heating 89, and the motors 70. Kitchen equipment 39. And then at the end, guys, this is how we left it, right? We left it where we put all these phase and neutral, and we allocated the load under each and every one of them. Now, believe me, when Mishad Kuli allow you to use this one, you probably will be senior designer by the time you start doing things like this. So this is not something that you walk in and you start doing load calculation for a building. But if you know it, you are on a track to become a senior designer and do all this good stuff. That's why we do it here in details versus Mishad doesn't have enough time guy to sit and walk you through all this stuff. Am I making sense here, guys? We allocated, I'm going to go just service panel will see everything. So under A through B, E lights, we allocated the load based on the phase and neutral under each one of these panels. I want to finish with the following. I would like you guys to pay attention to the numbers at the bottom here. These are the numbers I'm going to be using now to size the 5, 6 things that we talked about. In the whole calculation, guys, is to size panels and service panel and all the other panels and the feeders and the circuit breakers. That's why we did all this mess. All right, gentlemen, let's start with the service panel. I think this is where we left it. Can somebody verify? That's where we left. Okay, service panel. Let's go to Mrs. Service Panel. The service panel. Now, I want to remind you guys, the total load for the service panel was 497.4 for the phases. Can you see it right here? 497.4 for the phase. Okay, so everybody understand where we are bringing, Okay, I thought we did that one. Did we do it? The service panel?
No, that's what we're.
Okay. Okay. Is it done for you?
Yeah, how's that?
Oh, I just forgot to erase it. That's oh man. Now how are you guys gonna write? Oh, that's what I thought I didn't do it. I forgot. Usually I go erase and these and go over it. Okay, very easy. You take the 497.4K divided by 28 times 1.73. Everybody knows why? We're finding the amps. Yep. And that's the amount of amps that you can do. 1383 amps. 1,383 amps. Now, do me a favor. Then you're going to go take this. Can you guys see this? This book, you don't have it. I will make sure that you guys have a copy. I should have done that one. I'll give you a copy. Well, it's really one page that you need. It's not the page that you need is I'm short on time, but I will make up. It's very easy, guys. I'll walk you through how to use it. This is where you find the sizes, the actual panel sizes. That's all. Okay, so you take 138. Now remember, number one is a panel. We need a panel or a switch gear. So 138, 1383 amp. Take it to DW is D wall. This book. When you see a DW is what? D wall. Page 3-13. This is the page you're looking at right here. So when you go there, and I'll walk you in a second through it, it will tell you that they don't make 1,383 amps panels. You have to go to the next standard, which is 1,600 amps. Very easy. That's the panel. That's the box. Okay, now inside the box, we're going to put the circuit breaker, right? Inside the box, we're going to put circuit breaker. This is number one. Number two, overconduction device. Guys, go to 240.6. Now you have. That's an EC code book. Go to 240.6. 138, 1383, 240.6 give you 1600 amp. That's the standard circuit breaker. Yes, sir. Yes, I divided 497.4K thousand divided by 28 times 1.73. Cool. So what size panel do we have, gentlemen? Switch gear or panel. We have 1600 amp panel, and what size overconduction device inside it? 1600. Almost always, guys, the size of the circuit breaker and the size of the panel will be the same, but not necessarily. You could have a 400 amp panel protected by a 200 amp circuit breaker. That's okay. That's why you always, when you become an engineer, you're always going to look at the size of the panel and the size of the overconduction device. Smart engineers make them match. I mean, size your system so they can match. That's the best way to do it. Okay, so they go ahead.
I was gonna say, when I worked at the place repairing those, a lot of times they'd have a 800 amp breaker inside a 1600 amp frame.
That's a feeder. Yes. Yes.
into the panel, whatever.
Yeah. Gentlemen, and you're jumping into the industrial. These big circuit breakers have not just one size that you have to pay attention. They have three sizes. One is called the frame. That's a box, how much you can fit. The other one is a trip. Can you see the trip unit? And then the settings. So you can make this circuit breaker is 3200 amp. I can make it trip at 100 amp. I make this 100 amp by manipulating the tripping, the electronic in it basically. So let's keep it to the industrial, will ya? Okay, no, that's okay. All right, so any question guys about, now we sized the panel, the service panel, and we sized the overconduction device in there. So you go to Color Hammer Square D and say, hey, I would like you guys to give me a 1600 amp panel with a main circuit breaker 1600 rated for 28123 phase. Done. And they will tell you, no problem, give us $10,000 or so. It's a big boy. All right, let's go to the service entrance conductor. Everybody knows what, oh, by the way, do you guys know the little numbers here? The 6.1 and 6.1, 5.2? These are the numbers here on the side. Can I get you guys the 6.2 and 6.2? Can you guys write yourself a note? These are from a load calculation sheet that you will be doing for the industrial project. Okay? So later on when you do it, you say, oh, Chad, walk us through one thing. How am I going to match the two together? I just added these numbers there. So when you, 6.2 is equivalent to basically 3 here. Okay, let's go service entrance conductors. Now, service entrance conductor, guys, match, typically we go match over conduction device. Match over conduction device. Okay, so I have 1600. Now, do me a favor, 1600 amp. Can you guys go to 310.15B16 and find yourself a 1600 amp, 310.15B16, table 310.15B16, and find yourself a 1600 amp. Brandon, do they have 1600 amp? Look at the under 75 degree column. Oops. What would you do? 310.15B16. Okay. Did you guys, did anybody find a cable that can carry 1600 amps? You have two options. Either you sit and cry or parallel. What would you guys do? My son will sit and cry. You guys would not. So you parallel. So everybody knows what a parallel is? Parallel, guys, is when you grab two circuits to carry the same load. Here's one circuit. Basically, you have 3 phase here and a neutral, and a 3 phase here and a neutral in 2 different conduits. And they will be sharing, if the load is, say if the load is 400, this will carry 200, this will carry 200. That's what paralleling means. Parallel, yeah. Did it sound like something different? No. Oh, okay. That's the accent coming in here from the copy. Parallel. Parallel. That's a bad word. when you parallel, you want to still coming bad. Okay. The paralleling, gentlemen, when you parallel, you want to hover around 400. And I'm going to tell you why 400. Go look at 400. Give me a feeder for 400. Under 75. 600 kcm. You don't want to pull larger than 600 kcm because the electricians will be cursing you and effing you as they pull these conductors in conduits. It's really hard to pull them. So we try, can you? Yes. Should you? No. So we hover around 500 kcm, 600 kcm when you parallel. Okay, so that's, do you guys understand why I would like my answer here to be close to 400? So think about this one. Divide this one by what? What to get you close to 400? 4, very easy. 4, and then what does 4 means? 4, gentlemen, means 4 of this. 3 phases neutral, 3 phase neutral, 4 cables, okay? Good, so that'll give me 400. So how many sets am I running in different conduits, paralleling? Do you guys know what paralleling is? At the end, they take phase A, that the 4 conductors of phase A, phase 4 conductors, they tie them together like this. And they attach them to the breaker from one side. From the other side, the 4 conductors of phase B tie them together and tie them to the panel or the transformer from the other end. And every phase the same way. Phase A, phase B, phase C, each phase will have 4 conductors and a neutral 4 conductors. Okay, so very easy, piece of cake. Now it's piece of cake. Now we take the 400 amp and take it to which table? Table 310.15B16 under 75 degree column. Anybody knows why 75 degree column? Anybody remember that? Well, you always, they're coming from outside. Most likely it will be THHW, which is 75. But it's more than 100 amp. You remember, guys, more 100 amp, you always default to 75. Okay, so what size conductor? Here's how we write it. I have 4 sets. Everybody knows what a set is? Gentlemen, you're looking at a set right here. Here's a set. That's called the set. Can you guys see it? Set. 4 sets. Each set is going to have how many conductors? 3 conductors, 600 kcm THHW. This is your S. So, gentlemen, what you're going to do, you're going to have 4 of these, 4 conduits like these. Each conduit will have 500 kcm inside it. Imagine 4 conduits. Each conduit will have 400 kcm conductors. 600 kcm, 3 conductors, 600 kcm inside it. That's what we're doing. Now, somebody will ask me, what happened to the neutral, Chad? We need to go size the neutral, right? You need to go size your neutral. So we'll size our neutral. Any comments, guys, questions about that before we move? 4 sets, 3, 600 kcm, THHN. Piece of cake. These are the phases. Now let's go size the neutral. If I want to take you guys back, do you remember the neutral load on the service was smaller as expected than the phases because things are balanced, which is always the reason why we use 3-phase. So you have 2 options. At Michaud and other firms, guys say, you know what, we're going to pull full neutral. You know, when you hear them saying full neutral, we're going to make him in trace 3 conductors, 600 kcm. I'm going to make him 4. Call it a day. Done. You're good. Other, especially contractors, say, well, we can use the code to get smaller conductor, cheaper installation. Did you guys see why they go smaller conductor, cheaper installation? And that's what we're going to do at the bottom. Okay, what was the KPA for the neutral, gentlemen? Everybody remember? It was 299 point what? 0.8, I thought. Is it 8 or 4?
I think 4.
4. Okay. I have 0.8. So I'm right and you guys wrong. Let me see. Oh, 0.4. No, you guys are right and I'm wrong. I don't know why I have 0.8 here. So, by the way, would 0.4 kW make a difference in this calculation? Anything less than a K, guys, a K or less, in the size of service this is meaningless. So don't sweat it too hard. 0.4 K. Now if you're doing control, a K is a huge. 1 K is a huge transformer for control. For power, a K is nothing. Okay, divide this by what? 208 times 1.73. Anybody knows why? Because the neutral load will be balanced between the 3 phases, right? When you guys do this math, you're going to get closer to this number. 833 amps. 833 amps. That's your amps for the neutral. Okay? So that's my amps for neutral. Do me a favor. Can you guys go to NEC 220.61b? 220.61b. 220.61b. 220.61b, guys, if you read it, B, highlight it please, it will tell you, hey, if your neutral is more than 200 amp, 220.61b. 220.61b. If you guys read it, it will tell you that your neutral that you're calculating can be actually cut again. You can cut it one more time. Reduce it, Brandon. Reduce it another 70%. If you guys read anything more than 200, if you read it, you can reduce it 20%. So here's what we're going to do. We take the 833 amps, apply the demand for it. The first 200 amps shall not be touched. Then you come over here. Anything So 833 minus 200, cut them by, multiply them by 0.7, and add your answer, and you should come up with 643 amps. Now what the heck is chat with plus? The first 200 amp are, leave them alone. What they do in this section, whom am I going to pick this time? So my friend, because the neutral, guys, is highly unlikely the equipment will be on at the same time, they allow you more to derate the neutral even more. So how do you derate it? You leave the first 200 alone. So Jay, my friend, after you take 200 from your amps, cut the rest by what? 70%, and add them up. Everybody knows what this math, fuzzy math is. First 200 plus the difference between these two multiplied by 0.7. I did them all in one step. They allow you more derating. Okay, so now here's the amps that you guys want to do. This is my amps that I came up with. So then you take this amps, 643, divided by 4. Anybody can tell me why I want to divide this number by 4? Yes, you guys are awake. Am I the only one who's not awake here? So Gary, if you parallel the phases 4 sets, the neutral must be what? 4 sets. Can you parallel the phases 4 sets and the neutral 2 sets? No, they have to match. Because you're putting them in the same conduits, guys. Remember, they're here. Here's a 3, here's 1 set. Can you guys see that? If there's another set, they must have a neutral in it. Here you don't pull a ground because you're coming from the service. But yeah, if it's a feeder, you'll have a ground within each one of them, in each conduit, if needed, if you're using PVC. Now, if you're using EMT, you don't need to pull a neutral. Yeah, a ground. Okay, so if you guys do the math on this one, 161 amps, okay? And then you take the 161 amps, take it, now we size to table 310.15 D16 under 75 degree column, and that will give you a healthy following. 4 sets of 1 conductor, each one of them has 2 odd AWG THHW. Okay, now this is the first size that you do. I would like you guys to do for neutral at the service. They allow me to do another calculation in neutral at the service. And so they allow you guys to use the following. I would like you guys to take 600 kcm, 600 kcm, take it to the following table, please. Table 250.102C. Go to 250.102C, please. 250.10C. Everybody can see that table? Everybody can see that table? 250, it's page 124. Can you guys see that? Do I need to start yelling and yakking so you guys can see it? Okay, let's go directly into it here, because that's a good table to know. All right. My God, we can talk about the code. Okay, which page did we say? Now what's gonna happen when I'm 65 if I can't remember now?
So I have a question.
Yes, sir.
You know, like last time we were doing stuff, I know it was for something different, but like when we took out, we'd taken out the 10 kPa and then later on we added
Yep.
it back. Do we not do that like with the neutral when we took out
No.
the
No. Craig, my friend, in the NEC code book, there's so many formulas, so many calculations. You always, that's why I give you guys the reference. That's on the test. Because you're gonna get confused. That's where you take the references and you have basically everything that we do. Write yourself a note. When you size a neutral, go to this and do this. When you size that was the rating for the receptacles, I think.
Yeah.
Yeah. When you derate for the receptacle, go to this and do this. And you bring it with you. Otherwise, I dare anybody to remember all this stuff. Unless you're a goofy like Chad that's been using it for 20 some years. Okay, do you guys understand? There's just a lot. That's why on the test, don't sweat it too hard. Write yourself notes, always. Bring it with you. And if you even get confused, ask me. Because there's a lot of derating. Okay, this table, highlight this table. Please highlight this table. You use this table to size the following. Please, please. You're going to size it. Can you guys see the word grounded conductor here? That's a fancy name for what? Neutral. So you size at the service. This is only at the service. Okay. Number two. This is number one. Number two. Can you guys see the main bonding jumper here? Okay. This is the one highlighted main bonding jumper. That's number two. Do you guys remember the main bonding jumper? We just talked about it. That bonding the neutral to the ground. Okay. Number three. Supply. Can you guys see that? Supply side bonding jumper. Number three. Supply side bonding jumper. I want to spare you a little bit. This is basically a fancy name for when you bring the service conductor, guys. Now this is non-metallic, so you don't do that. If that was metallic, when you bring the service conductor, they bond the conduit. They put a clamp on the conduit and they bond the conduit. That's a fancy name. The fancy name for it is supply side bonding jumper. So here's the conductors coming out of the ground. This is non-metallic, you don't bond it. But see if that was rigid. You bring the conductors coming out. Okay, here's my 4 feeders coming out. Going to the one of them is going to be a neutral for your faces. You color the neutral with white, yellow with color in the field. Then you take the conduit, you put the clamp on the conduit, and you take the conduit and you bond it to the ground bar inside your switch here, required by code for safety. Everything is grounded and bonded. So that fancy wire is called supply side bonding jumper. I'm sorry, this is system bonding jumper. This is the fancy name for it, supply side bonding jumper, which is number 4. So, system bonding jumper. Now, what the heck is a system bonding jumper? When you guys have a transformer that you own and operate. So, Brandon, when you have a transformer that you own and operate, and you take a neutral from your transformer and bond the neutral to the ground, your transformer that you own and operate, you bond the neutral to the ground. That bonding wire is called, instead of main bonding jumper, system bonding jumper. So main and system are identical. Main at the service, you do it right at the service panel. System, you do it inside the transformer that you, as an owner, own and operate, not the utility transformer. Okay, so gentlemen, 4 things coming out of this table. And by the way, this is brand new table, got born in 2014. So this is fresh for you guys. Before that, they used to refer you to 250.66. Okay. So now, when you they allow you guys to size based on the. Now look how this table goes. It goes by the service conductors. Okay. So we have how many runs? How many conduits? 4 conduits. Now we need a neutral in each conduit. Okay. So you size the neutral based on the conductor inside this particular conduit, right? So what's the conductor? The phase conductors. What was the phase conductor in each conduit? 600 joules. So when you do 600, of course we're in the copper business because we love copper, right? If you're in aluminum, we size based on copper. So good copper. So 600 will put you in this category, gentlemen, right? Over 350 to 600, and how the heck did that? So that will 1 up. So what's your minimum? Why not? Minimum, 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 minimum. Why not? What did we come up with before? 2 watt. So you choose the largest.
Oh, so that's just,
That's your bare minimum.
okay.
Shall be killed if you use less than that. Oof, that's harsh. Shall be jailed. You see what I mean? This is the bare minimum that you can't go below.
So if we got smaller than 1 odd, we'd have to go with 1 odd regardless of what.
Regardless what you came up with. That's the bare minimum. Am I clear about this? Very clear. The bare minimum. Okay. All right, gentlemen. So let's go here and let's write the bare minimum here. So based on this, my bare minimum was one conductor, 1/0 AWG, and it's going to be THHW. And now, which one are you going to use? Two. Okay, so basically, how am I going to make you guys understand that you choose? Can I say choose the largest? Choose the larger. The larger is better than the largest. The larger of the two. The larger of the two calculations. So you use the larger of the two. So which one is the larger? 2 watt. Gentlemen, you're experts now in that arena. Okay. So when you do that, 2 watts. Does it make sense? So that table gets you the bare minimum. So when you go to court, Gary, and you burn the switch gears burned, and you go to court and they hire Chad as a witness, expert witness, and I sit there and I look at, did he follow the bare minimum? Go to this table, I say, Judge, based on the secret book, which is the law of the land in Minnesota, by the way, it is the law. He did not follow the minimum. So put him in jail.
Oh, yeah. You're lucky it's only jail now.
It might be only a misdemeanor with 10 grand penalty. Sorry, Gary, we're picking on you today. Okay. All right, gentlemen. Then, this is how you parallel. This is your paralleling. So, this is your paralleling. The first one, can you guys see the first one, phase A, phase B, phase C, neutral. In each one of these conduits, you will have phase A, phase B, phase C. Black, red, blue. Black, red, blue. Typically, the phases for 28120 system. And white, I can't write white on white here. So I put green here. So white will be your neutral. So these are how you parallel. How many conduits do we parallel? 4 of them. Here's the 4. And then what do they do with them? They go from one side here and the other side, guys. They tie the phases together. So all the phases, the 4 phases of A on both sides will be tied together and tied to the equivalents. That's what paralleling is. Okay, so and then I'm going to write down here. So I have 4 sets. Each set is going to have 3 conductors number 600 kcm and 1 conductor number, what's the conductor? The neutral. 2 at AWG T, all of them are THHN, no, W. Anybody knows why we use THHW? Well, if it's service that's coming from outside, typically when they go underground. So when you go underground, you need a conductor, THHW. You need a conductor, the W. What does W stand for? Wet. Yep. Can I use THHN coming from outside? Not legally. No, you can't use THHN. THHN is only for indoor, dry location. Wet location, you need one with W at the end of it, like THHNW or THHW. Okay, gentlemen. Now all what you have to do, Gary, is grab your tools, Mr. Apprentice, and go put that system together. All these 4, we didn't size the conduits. Typically, later on we'll be sizing conduits. Now we go size the conduits. What type of conduits typically we do, guys? For this PVC Schedule 80. Here, so you're looking at it right here. I think this is Schedule 80.
You run outside, don't you need metal?
We're underground. Okay. Okay, how do you wire? Here's the rule of thumb. If you don't know how to wire, if you go underground, your conduit of choice. Now remember, you can do anything you want based on the code, but your conduit of choice when you go underground is what? PVC. Why? Anybody knows? Rust. Rust is the keyword. Underground. Am I clear about the word underground? This is your conduit of choice. Now, can I use rigid underground? Yes. Rigid steel will rust. Not a good choice. That's why you go with this PVC. Now then you can use galvanized rigid, but you're absolutely right. They use galvanized rigid. They use also PVC coated rigid on some of these, but typical.
Galvanized maybe was old school and that's maybe more newer.
Yeah, like I said, typical engineering projects. When you go underground, guys, you go PVC. You go above ground, you go two options for you. When you go above ground, you can either use rigid. If Chad's car is going to drive or run into it, that's called severe physical damage. If a truck is going to run into it. So for example, if you're putting a service right here, and there's a parking lot, and you're putting it against the outside wall, now could it be that so my friend came drunk one day and ran his car right into it?
Sounds like.
Could it happen? Yeah. So this is your severe physical damage. So what do you need for this? Rigid. They're thick. They're very thick. Now, if you don't have severe damage, which is typically indoor, you use the thinner ones, which is these little guys. They call them EMT.
That's what it was. Chad was underneath the parking lot.
Yeah, that's rigid probably coming. Here's the EMT, very thin. They look alike, but one of them is thinner than the other. This one is, still protect you, but not as good as the rigid. But you see kind of the default. Okay. Gentlemen, moving on. Let's go size the main bonding jumper. Now do me a favor, right? You guys in the same, that was changed in 2014. Do me a favor, go to the same table. Now you have to size it base table. 250.102C. Size the main bonding jumper from 250.OC. Everybody knows what a main bonding jumper is? Bonding the neutral to the ground. All right, how do you do it, Chad? Here's how you do it. How many main bonding jumpers do you have in the service? One. No, the main bonding jumper is just a wire. Now, neutral 4. Main bonding jumper is how many? 1. That's just a little jumper. Okay, gentlemen, the way they do it the following. What's the size of the conductor in each run? KCM. How many runs did we do, gentlemen? 4. You multiply by 4. And that will give you what? 2400 KCM. Okay? Now, step number 2. 2400 KCM. Is it more than 1100 KCM? Is it? Right, yes. Okay? Because that's a major question. So the 600 KCM is the phase size, right? You multiply it by 4 because we have 4 of them. Yes, sir.
Where did 1100 come from?
The 1100. If you guys go to table 250.102C, right underneath it, it will tell you, hey, if you exceed what the table is giving you. Can you see that? If you run out of wires, can you guys see note number 1 underneath it? Note number 1 underneath it. If it's larger than 1100 KCM, only if it is, do the following. So what do? You take that number, gentlemen. So you take the 2400 KCM and multiply it by 12.5%. Now where did that come from? Note number 1 under the table. Highlight that one. Note number 1 under the table, guys, will tell you if your math. Now, whom am I going to pick? John. John, what happened if the answer for this was no? Then you use the table. Okay. Okay. Let me just give you a hypothetical question. Can I? What happened if I did this math and I end up with 1000 KCM? Is the 1000 KCM more than 900 KCM? No. So where would you go to the table then? Directly to the table for 1000. What would you size for 1000? What would your size be? To what, gentlemen? Am I making sense? To what? Am I the only one who's excited about that table? Note number 1 underneath it. Okay. When, guys, now I know some of you are taking math, but you know what 12.5% of a number, right? You know how to do that. So that will give you 300 kcm. Okay. Now, is 300 kcm an actual wire size that they can sell you? Well, you said no, but you guys don't know. It is, maybe. How would you know if that number is actually an actual size before you order and they say, are you coming from the moon here? You're ordering a number that we don't make? Yes, this is what you're going to do. Then you take the 300 kcm, take it to the following. Chapter 9, please. Table 8, please. Let's go to chapter 9, table 8. That's where we do our check. Okay, so we haven't done that. I'm going to move it here. You guys got that? Oops. Did I move? Okay, you got it. 300. We're going to go to chapter 9, table 8. Let's go to chapter 9, table 8. Chapter 9, table 8. Oh, chapter 9. We're at the end. Can you guys see we're at the end? Right here. Chapter 9, table 8. Table 8. Table with table. This is table 5 all the way. You got it? Okay, table 8. Here you go. Jump. Table 5. Highlight this table, will you? We're going to be using this table for a few things. Highlight it. Talk about. Okay. Now, when you go, what did we come up with? 300. So can you guys go under wire size right here? KCM, wire size, AWG or KCM. So you can go from 18 all the way down, down, down. Do you see 300 here? Is it a wire size then? Yes. Now, if you came up with 305, what happened if I came up with 305? What would you do? Next size. You don't go down. Down is dangerous because it's less safe. You go up. So 300, you came up with 301, it becomes 350. Unless you're willing, like Chad, a registered engineer, drop the one and sign in 300, which you can. As an engineer, you can. But cover your butt type design, you go always to the next standard. Okay, so that's how we use this table, guys. So please highlight it. These are all the sizes. Obviously, we use this table for other things that we're not going to talk about at this time. It will give you also the circular mill for, this is where, so what happened if you came up, guys, with a circular mill of, let me just pick a one. We did math, and you came up with a circular mill of 100 kcm. 100 kcm. Okay. Do they make 100 kcm? 250. Oops, these are odds. So how am I going to check? And you guys see the kcm, right? Come over here. So from here all the way up, they give you also the kcm right next to them. Can you see that? There you go. So look at this. I need 100. Do they make 100? There's 3 right here. There is 85 and 107 kcm. So which one am I going to use? 107. Oops, I can't find just 107. Bam. There you go. So what size do I need? 4I. AWG. I have been asked this question in this class before. The students were asking me, Chad, what is the kcm for 350 kcm? Because, right, you don't see kcms here.
Did you ask him what color the red rooster was?
Exactly, red rooster. So if 1 odd, here's the kcm for the 1 odd, right here, 53.4 kcm. After 1 odd, everything in kcm. So 400 kcm, what's the kcm for 400? You don't try it because it will be 400 kcm, right? Everything is kcm. So don't ask me this question. I'm not kidding you. I was asked. And believe me, I would have asked this question when I'm new to that. So I'm not judgmental. When you're new, you're just confused. And people get confused. Say, Chad, I can't find the kcm for, I think it was like 500 kcm. because it is in KCM. After 4 out, we switch to KCM. No problem. People get confused all the time. So what size, gentlemen, then? We verified, what did we do? We verified that this one is one conductor, 300 KCM. What insulation? THH. Now, since it's inside the switch gear, since it's inside the switch gear, guys, and it's bonding, this is bonding. You can THHN or THHW, or how about bare? Do they spell bare right?
B-A-R-E.
Yep. As in naked, bare, or bare conductor. Yeah. So you can have a bare. Now remember, this is a bonding conductor. It's not carrying current. It can be bare. It can be insulated THHN or THHW. Doesn't matter because inside the switch gear is a dry location. Or it could be bare, or it could be covered. Everybody, you guys know the difference between covered and insulated? They look alike. So you look at a conductor, it looks like insulated, but they have a cover. The only difference is the thickness of the insulation. So you hear, for conductors, they have 3 options. Either bare conductor, you don't have insulation in it, like this. Insulated, it looks exactly like this. Or covered, it looks exactly like this, except the thickness of the insulation is smaller. Why would they do covered? To protect it from the elements. If you put conductors outside, they cover them from the sun and the elements, but they're really not meant as an insulation, meaning don't grab on them, because it wouldn't insulate you from being electrocuted. Okay, gentlemen. Grounding electrode conductor. Let's do grounding electrode conductor.
Change that table to
Okay. Any question about the main bonding jumper? Good. Grounding electrode conductor. For grounding electrode conductor, hold your horses. For grounding electrode conductor, you do the same math, the following. The same math. 600 KCM times 4 equal 2400 KCM. Then you take the 2400 KCM, take it to table 250.66. Different table. Only this year, guys, they made a different table. It used to be one table. Remember that one that got born this year? 250.102C got born. It's actually, we cloned it from 250.66. Okay, so if you go, do I need to use 12.5% Brandon here for the grounding electrode conductor? No, you don't need to. So if you guys go to 250.66, what size would you, please go there and highlight that table. So you're going to end up, my friends, with one conductor, the largest, which is 3-aught, AWG, THHW, or bare. Can I emphasize, guys, when you deal with ground, when you deal with grounding and bonding, who am I? I didn't pick on Tony today. Tony, when you deal with grounding and bonding, the conductor can't be bare. They can be what? Bare. No insulation there. Or insulated. Everybody use 250.66.
So the only reason they created that table is for like main bonding jumpers and stuff?
For the 4 things that we talked about. In the past, guys, before 2014, it used to be, this table used to be for everything. For the 4 things that I told you about, the neutral and the main bonding and the system and the supply, as well as the grounding electrode.
Yeah.
Apprentices like my friend Tony used to get confused. So they split them. Rightfully so. They put 2 tables. They're almost identical though. All right, grounding electrode conductor. I remember those guys are coming soon, so I need to, and then I'll give you guys a break quick before. Now, I'm going to switch it to the receptacle panel. Do the same thing for the receptacle panel. What did soak? Did it soak? You got soap?
Oh, wow.
It's magic. I didn't even notice.
Sneaky. You're sneaky, man. No one
Don't you have the?
Oh, yeah.
Grandma diaper.
Depends.
Okay. Can somebody verify that the panel size? Now we're doing receptacle panel, gentlemen. What was the load for the receptacle panel? It was 95.9 kcm. Where did I get this number from? That big, nice table? So,
KVA.
I told you one of us sleeping here.
Uh,
KVA, thank you. Divided by 1.73 times 2A. The whole system is 2A. When you do your math, guys, you're going to end up with 267 amps. Now you take your 267 amps, take it to DeWalt. Everybody knows where DeWalt is? Right here. That's where they give you the size of the actual size of panels. I'll give you a copy of it today. When you go there, it tells you, oh, by the way, they don't make this. The next standard panel is going to be a 300 amp. Done. Can you guys see we're repeating the same steps now for the second panel? All right, gentlemen. Overcaptation device. Overcaptation device, take it. You go to 240. The same thing. You take the 267 amps, take it to 240.6, and if you guys go there, it will tell you, hey, by the way, they also don't make it. You have to go to what? 300 amp. So now my panel and my overcaptation device match. Brandon, that's where you want. Now, could it be that this will be 250 and the panel will be 300? Yes. So when you get into a situation like this, guy, try to match the panel. It's a good idea to match your panels, if you can. Okay, so 300. Questions? Now we're going to repeat the same steps that we did for the service, guys, for all these. It's very easy, repetitive, basically. So, cool. Yes, sir. Thumbs up. I told you, raise your hand, you buy, man. Feeder conductor. Number 3 is sizing the feeder. Excuse me. Sizing the feeder. Okay, the current that I need to size for, guys, it was, where am I? So we are into, okay, the panel, I'm sorry, okay. So 267 amps. I need to size a conductor for 267 amps. Now, feeder overcaptation device, 267 amps. Now, the way I typically do it, guys, my overcurrent protection device. What was the overcaptation device for the panel? 300 amp, right? We just did that. Match the overcaptation device. When you size the conductor, one more time. When you size the conductor for a panel, here's the amp that you need to size for. But instead of using the amps that you calculated, always match the conductor to the overcaptation device. That's kind of engineering way of doing it. Now, so match overcaptation device, match the conductor to the overcaptation device. Then I have 300. Everybody knows where the 300 came from? Take it to table 310.15B16 under which column? 75-degree column. On the 75-degree column. And that will get you what conductor size again? That will get you one set of 3 conductors, 350 kcm, THHN. Can anybody tell me why THHN? We're pulling an EMT conduit like this, indoor, so THHN. It's feeder. Where do you put the feeders typically? Indoor. They're not coming from outside. Okay. Where's my neutral? That's next. Where's my neutral? My neutrals, these are 3 phases. Let me know when you guys are done. Can you guys highlight match overcaptation device for the feeder? Match overcaptation device. OC, overcurrent protection device, OCPD.
What's under the 315 there?
75 degrees.
75. I always write 75-degree column, guys, to emphasize that you always go to which column? 75. So when you go to the table, you can see where I put my arrow. Right underneath it, I put a column. Because when you go to the table, which column are you going to use? You know, 75. If, Jay, when you're in the industry, if you say you always go to 75, you're right 95% of the time. Now, when you talk to your wife, I don't know how many percentage of the time you're right, but I tell you, that's much more than I am right when I talk to my wife.
Uh-oh.
Oops, we're recording. Huh?
Oh, yeah, you're held accountable for that one.
Sorry, honey.
Better bring up the
Okay, the
audience.
neutral. The neutral. Either neutral conductor. You guys remember the amps for the neutral, 56.9 kcm for the neutral panel, the same as the phase, right? Divide by 1.73 times 2.8, and that will get you 100 and what? Let's see. Why do we have the receptacle panel? Is the receptacle panel smaller than the... Yeah, the size is smaller. I think there was some three-phase we put there. We put some three-phase in the receptacle panel. That's what the size is smaller. That surprised me for a second. Okay. Everybody knows where the 56.9 came from?
Yeah.
When we did the math, there's some three-phase we did not include in them. Okay, so I'll give you 158 amps, gentlemen. Now, you guys remember when we do the neutral, we also apply this 220.61. Okay, so the answer is 158 amps. Is it more than 200 amps? No. Do I need to derate the 70% that we did for the neutral? No. No, so I don't need to derate. No derating. No derating. Then you take 158 amps, gentlemen. Take it to table 310.15 B16 75-degree column, and that will get you one set of one conductor, 2 aught AWG THHN, and
Please have 158 is greater than 200.
ah.
I know that.
If you go to 220.61, it will tell you if your neutral is more than 200, what do you do with that? The portion that's more than 200, you guys remember? The portion that's more than 200 in the neutral, you cut it 70%, right? So I verified that's not more than 200 here. Because if it was, Brandon, what would you do? The portion that's more than 200, cut it by 70%. Okay, gentlemen, here's your phase A, phase B, phase C, neutral. And that's basically how your conduit is going to have. One conduit, three phase. The phases are going to be 350, I think, right? 350 kcm, and the neutral, 3 conductors, 350, and 1 conductor, 2 aught, right? Right here. We might be able to smuggle another panel, guys, before they come. Let's go equipment ground conductor. For equipment ground conductor, number 5, equipment ground conductor, go to 250. Let's go to this one. 250.122, guys. Table 250.122, please. I don't know if did you guys use these table when you were in the second semester? Some of them you did, some of them you don't. So that's why I like to flash them, just in case. 250.122, 122, 122, 122. Page 131. Okay, 122, not this guy. 1212, this one. No, not this one. Did I see? Page 122, way at the end. I hate where they stick it back here. There you go. Now, how do you use this table and for what? Highlight it, please. You use this table, guys, for equipment ground conductor. Now, what is that fence mean for what? For the ground wire. That's a fence, none. Who said neutral? Do you want you and I to get into arguments here? Not neutral. The grounding conductor. When you guys have electrical circuits are made out of three things. 5 conductors in an electrical circuit. Typical electrical branch circuits and feeders are made out of 5 conductors. There you go. You're looking at them. You're going to have 3 conductors on the phase, every circuit, which is typically colored conductor. The white conductor is always what? The neutral. So 4 conductors, 3 phase and neutral. And then the green conductor will be what? The ground. Now, if you're putting it in a PVC, you need the green conductor. If you're putting it in an EMT conduit, the green conductor don't need it because the conduit itself will act as a green conductor. So this is called, the technical term for it is equipment grounding conductor. That's why the frame of that fixture, lighting fixture, you tie the frame to this wire. So if Chad is changing the ballast there, and accidentally, if you don't put this wire, this is only for safety. The ground is for safety. So if you're changing a wire and this fixture is not grounded, and accidentally the phase touched the frame of the fixture, now the whole frame is hot.
Yep.
And Chad is standing barefoot in his basement. Look at that. Make it fatal.
Yeah.
Make it fatal. Barefoot in the basement and put 2 inches of water in the basement to make it wet really good. Barefoot standing on a metallic ladder and grab into that fixture. This will send you straight to Jesus, right to the Lord. No, straight line, man. That type of a shock. Yeah. Now, if you're standing, if you put your boots insulated and you touch it, you'll get a little shock. You shake a little bit, you know, but you wouldn't go that direct. That's why we don't work barefoot in a wet basements, right?
Work Crocs.
But imagine the public. Can you tell how many times my wife and your wife go to the basement barefoot and they grab a fridge in the basement, the handle like this? How often do we do that? I do it all the time. And my wife and my kids. Now, if that frame is energized, that's a fatal. See why we do it? It's not just for the people who work on it, for the public. This conductor is God sent to you, the equipment ground conductor. All right, so you size it based on overconduction device, guys. Very simple, very easy. So what was the size of the overconduction device?
300.
Was it 300? Here's 300. Again, Chad loves copper, so we go to copper. So what was the size? 4. Could I have used the aluminum too? No. Yes, you can use aluminum, number 2. But typically, if your conductors are copper, everything will be copper. So number 4. That's it. So that's how easy that using this table is. No gimmicks, nothing. So we can go right here, gentlemen, and equipment grounding conductor. What do I check here? Okay, equipment ground conductor. We have 300 amp, right? 300 amp. So you take your 300 amps. 300 amps. Make sure you take it to table 250.122. And when you go there, it will tell you one conductor number. Anybody? Number 4, AWG, and typically THHN. Now, it could be bare, but typically when we put them in a conduit, guys, it's insulated, like the others. Sequence have the insulation on it, the green. So, what size conduit do you want? 2.5 inch EMT. We haven't sized the conduit. Do you guys size conduit yet? I'm going to wait sizing conduits until I get you this beautiful baby here. And first, I'll make you guys size by hand so you can get frustrated and stop yelling on that thing. And then we use this boy. God said to you, plug a couple of number, any size conduit can come right in here. Unreal. Electrical calculator. If you're an electrical contractor and you don't have this one, you don't exist. Yeah, there you go. That's called electrical calculator. It comes part of my curriculum next quarter, guys, for you. Great. You sit in your truck and you're going to size how many conductors, size, bam, 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 done. So you can pass it. It's you put it in your Christmas list. It's $62. So if your grandma wants to give you something, John, this year, or grandpa, but electrical calculator per recommendation from Chad.
Still need
Put it.
socks.
Need socks.
That's for socks every year.
Yeah.
I was losing them.
We do have time here, guys. Let's kick the lighting panel quick, because lighting panel we're now repeating ourselves. You guys are becoming experts now here. Let's do the lighting panel, shall we? Okay, lighting panel, guys. The load for lighting panel was 242.5K. Divide this by 1.73 times 208. That will get you a healthy 674 amps. Take yourself to 674. Go to DeWalt. That'll get you an 800 amp panel. 800 amp panel. Okay, overcap protection device, same thing, 674 amps. That will get you 700 amps. Can you guys see the difference? Now I have a panel 800 amp protected by 700 amp circuit breaker. Is this okay? Yeah, no problem. You can see that with the difference now. Brandon is an engineer. He said, you know what, Chad, I want to up the overcap protection device to 800 amp, match it to the panel, and size everything for 800. That's okay. But for the process, this is how you guys go. Size it, 700. Okay, cool, good. All right, let's go size the cable. Am I going too fast? Now imagine if you have to write everything. Now that's why I give you that little sheet, guys, cheat sheet. Okay, so lighting panel, feeder. My feeder, guys, the size for the conductor 674 amps. I always say engineers match overcap protection device. Match overcap protection device, which is 700 amp. Match overcap protection device. So 700 amp. Jay, do you think your table have a 700 amp cable? I guarantee you it doesn't have. So what do? Parallel. When you parallel, how do you start, guys? Start with 2 sets. If 2 sets doesn't give you 400, around 400, then add a 3rd set. If you still don't get around 400, add a 4th set. If you still don't get, you add a 5th set. You know what I mean? So here, very clear, if I put 2, that'll get me what? 350. This is around 400. I see around 400. Then gentlemen, so then I take the 350 and take it to table 310.15 D16 under 75-degree column. This will give you 2 sets of 3 conductors, 500 kcm THHN. Done. Here's the size of the feeder that's going to your lighting panel. You see how easy that is, guys? Now, what they do at Mishad, Brandon, they have their own tables that they did this calculation and they say, this is Chad's business, man. We don't have time to do this monkey around. If this size is this, use this. If this size is this, use this. But it's nice for you guys in school to know how it's done. You know? Yeah, absolutely. Because you would be one day the senior designer going to review these, update them, adjust them, verify them. So, okay.
Pulling the numbers from.
That table that we had.
310.15 B16 75.
Are you talking about the first numbers or the one?
Well, the original number for every single one.
The original number is on the table we had here.
Which numbers are you talking about?
Last week when we did the silver.
What are you doing here?
Yeah, it was. Yeah, but
Which
I mean,
number are we talking about? The number that I'm
the original number you start with each problem.
I see what you mean, right here. Right here. No. The original number is right here. Right here. Do you see that one? So I'm doing number 3. Number 3, that would be that feeder, which is basically right here too. Now, these will repeat itself for these two. See what I mean? So that would be, we did one for the receptacle, now we did one for the lighting, now we did two for the receptacle when you do for the lighting, and three for the receptacle, three for lighting, and when you do it for this. So one, two, three, four. Huh? These are the numbers
I
that.
suppose they'll be given in like a computer.
Yeah,
They'll be given.
absolutely. Okay, last thing. Neutral. Let's do the neutral quick, guys, before our friends come here. The neutral. The neutral size, guys, we have 242 kcm, 242
KVA.
What's with the kcm today? 242.5 kVA divided by 1.73 times 208 equal 674. We just did that, right? Now the only step that you do is you take 674 amp and you apply the rating. You guys remember 220.61 rule? You apply it. So it says 200 amp, leave him alone. Higher than 200 amp, 674 minus 200. Multiply them by what? Anybody? 0.7. Add them up. And that gentleman will get you 532 amps. Remember that over 200 amp, we can derate them? Okay, now we need to parallel. You take the 532 divided by 2 because we're already paralleling 2. That will give you 266 amps. You take the 266 amps, same table, table 310.15 B16 75 degree column. That will get you two sets of one conductor, 300 kcm THHN. So your neutral, your phases were 350. Were they 350? My phases, what was the size? 350, and my hot is my phases were 500 kcm. My neutral 350. 300. So the phases were 500 kcm. The neutral is a little bit lower, typically 500 kcm, 300 kcm. Huh? One last thing, and I'll break you. Just one last thing, not break you. I'll give you a break time. The equipment ground conductor. This is the equipment ground conductor. Take the 700 kcm guy. Equipment ground conductor. Take the fuse, the circuit breaker size. Take it to the same table, 250.122. That will get you one conductor. Number what? Number 1 at AWG THHN, and and then can you see where it's going to be inside? You will put the conductor inside each one of them. So that will be basically here 2 sets. So your answer should be the following: 2 sets for total. 3 conductors, 500 kcm. 1 conductor, 300 kcm. And 1 conductor, 1 at AWG. In every set. Am I making sense? 2 sets of the following. And here's a Gruber here. Hey, how are you guys? Good to see you. Hi there, how are you? We're done. This is good breaking time. Come on in. Good. We're upsizing the panels and paralleling. Now you guys gonna correct me here, huh? Not my students. Let's give it a break. Do you guys mind if we can? I was grilling you. Can I give him 5 minutes break here? Yeah, that's what you said. Okay, thank you. That would be great. All right.